Okay, good. Thank you for being patient. All right. All right, Nadia, what can I do for you?
I don't know if I should do the live or just do the
Do the open to the sentence. That's what's in there for you. It's the same one they did yesterday. So just go to the density lab. Okay? Open it up. Okay? So, for example, here are your objects. We've made those observations. I put these numbers in here for you. I took the data for you. In this table here, you can put all those numbers. Okay? When you do that, well, the green line is the line that does represent the density. But what about the green line actually represents the density? Okay, so what is F? Okay, but what is it actually? Okay, slope is rise over run. Okay, you got these first. Okay, because this is what rise. Volume over run. Mass over volume is. So that's what slope is. Rise over run. That's why we have to have mass over that's y-axis. Okay. Your sheet. Where is it? Which one specific? Which one? Represents the density. Okay. So go into the Google sheet. For that question, which what part of please put that into the sentence. So what about finding you can include it that way? Okay, but actually it's the same. These are not the two that we determined. Okay. So we are looking at the chart. You need to update the maximum rate of access with labels and units and the type. You go back to sheet one, which is this is going to be your x-axis, the unit, y-axis, and the unit. Okay? You need to write type. If you highlight this whole table, okay, so click on highlight it, you control C on your keyboard. You can go into your lab now, and you can control V. Takes the leaves. There you go. It's in there for you. Okay. How many? So. All right, till later. I did. I wanted to get the poster. No.
I wrote this down. Because when I
Yeah,
it makes it sound
There's an explanation behind it.
He's supposed to ask right about God.
keep up.
So for
You
these
understand me?
two,
But I mean, is it serious?
they may vary a little bit, that's okay. But
That's
that's also
pretty
why
obvious to me.
you
They would turn your head.
Right.
that means they're
Okay.
Which is funny because that's why it says like very born
Very nice. Okay.
Yes. You can do copy chart.
Whoa. Whoa. Holy smokes. We do enjoy my music.
Okay? Now, when you were talking, that is the
This is
thing
actually the
where-
first time. And that's just Huh? Yeah. This is real footage.
Wow, you screamed
on me. Raw footage. Yeah.
That number though, it's just like this. All
Yeah.
the
Just like
rest of
like
it,
the pop star
they got-
dance.
That's one of the ways that the density that's-
Yeah, well, maybe it's not
We can open the lines, so they can that density faster.
Yeah.
Oh,
I really
okay. Now, the other thing is you have to go down to the components. Here, what I want you to do is each individual one number. Okay, so it's actually a million, and divide them from that figure. Give me what the, we would need that one. Okay? By doing these forms, find the average of them. By having all four of them up, and dividing by 4, that would be 12, so there's 4
Yeah,
values.
yeah.
That would be the average density.
You ready yet? Yeah, hold on.
Doing the math, and each of these are
Nine. You're not coming on 9.
well, you have to do all 4. 1, 2,
In the
3,
morning.
So these
Oh.
are the smallest drop. Take 10.15 divided by 5. That's what you put in that table. Specifically like part of the graph. I mean, the slope of the line on the graph.
This is also. Let me see your guys. Where's my?
Okay, take off the FLs and the G's in next G.
Oh.
Because you put in FLs, you cannot graph.
I thought it was going to be electric.
No, that's why we put them up above there. Okay?
We're not being.
You can't. On the other sheet, it's fine because that's not graphing the material. But when you put letters in with numbers in Excel or in that, you can't graph. So now that you take it off, now you got your graph.
Where'd you have this?
Well, you need the table from that Google sheet.
Oh.
And you need the graph. Now your graph is not done yet. Yes, you do.
So I need to.
Right in there. That green line is the trend line. There's the formula on the trend line. So that's you just need to put your labels in your units and your type. Customize, chart access levels. Chart title, change update to whatever you want it to be. Well, remember, it should be what is on the x-axis versus what is on the y-axis. Okay. So that's always the way we do. Okay.
This is math.
Well, you have to decide. Density is a
Wait.
property.
This is
No. Is that better for identifying something than saying quality? Quality. Okay, why? You need to say
You're just trying to
density would be a better property. Okay.
Saturday.
3:30.
That's not always.
If I get this problem here.
Bye, really.
That's like,
So we thought the average multiple cycles. That's what like.
I can't promise it. I would say, I can't promise.
What about the graph?
I'll let you know when we get there. What about this?
But
They
that's not
forget.
actually a graph.
I'll put that picture in here too.
Go back to your graph.
I'm not being married.
Back to your graph.
I will not be
Your
married.
graph.
No,
Down.
Huh?
Not there.
Burn?
What about the
I don't
graph?
care. Somewhere. Anywhere but married. I will not.
Okay.
Because
so
I
what if
cannot
you put-
stand the thought of being that far underground in those.
Sure,
I'm
because they're
dead.
gonna-
I'm not doing that. I'm just gonna be eaten
Well,
by
The
bugs.
slope of the graph.
Do not do that.
Slope of the graph.
Don't even talk about it.
Slope is
Sick of it. I'll be married though.
the way we set up our graph.
Enjoy yourself. I'm a bear.
This graphic material is when we
Where is it?
graph the points.
Are you gonna bring your friend in?
The other way was if you average four numbers. The density of-
You're getting dragged down.
No, I'm not. Boy. He is.
Okay, I thought we were still on the question, so what's the next question? So what
Well,
part
you
of
said
the graph
I will
tells
tell
us the
Even though I'm already dead. I will come back.
Come back to speak or something.
which is the epsilon of the. It's not a slope of a graph, it's a slope of one thing. Yes, you do.
We're into this.
What is this
That's
called?
why-
It's like that, that's what it is.
Okay, Ryan, good, good.
Yes. I would like you to.
All right, let's talk about your conclusions quickly.
You're gonna put that away before you have to put it up in there. We'll do it on your computer, not on your phone. Okay? Put it away.
All right. So, ladies and gentlemen, let's talk about your conclusion real quick here because Cynthia asked a great question and I want to make sure you understand what I want you to do. In the conclusion of your lab, ladies and gentlemen, what I expect you to do is write a conclusion where you have found the density of this two ways. You have found it. I don't want that. You have found it by graphing it, and you have found it by taking the average values here. You have two numbers. I want you to compare both of those numbers to what you should have gotten. Now, again, how do you know what you should have gotten? You had a certain color sample that you wrote down. Okay? So up here in the original observations, you wrote down what color sample you had. Silver, white, green, red, whatever. Down at the very bottom, under the conclusion, there is a table that tells you what those were supposed to be. And again, as we talked about yesterday with Levi, some of these are to 2 sig figs, some of them are to 3 sig figs. That doesn't matter. Your numbers are based on sig figs based on the measurements you made. But when you're comparing your value to this one. So on your graph, what was the slope of the line and how does it compare to 0.77 if you had the tan wood sample? This is what you should have gotten. How did yours compare? And then how did your average compare? Was your average about the same? Was it a little higher, a little lower? And you have to put data into your conclusion. So I would expect, ladies and gentlemen, to see 3 numbers. Here's the number I should have gotten, 0.77. Here's the number my slope was, 0.79. and here was my average of the 4 samples, 0.76, whatever it is. And then you interpret if your numbers were close or far away based on your opinion. I cannot downgrade you for your opinion unless you are telling me that 0.1 is really close to 0.77. That isn't right. Okay? So you got to use your best judgment. Was your number close to these that you should have gotten? Okay? So that is what should be in your conclusion. 3 numbers, what you should have gotten, the known value here, the value from the slope of your line, and the value from your average of those 4 samples. And then something that tells me how you think those compare. That's what I need you to do in your conclusion.
So you do this in density for those four.
Yes, ma'am. Okay, it is just that first number in front of the x. That's the slope. The other one, it would be the y-intercept, and we don't really need that for this particular level.
That's just the average of the density.
You should.
Oh, 2.31. Yeah. The slope from there, and that's supposed to be scaled.
Do you do not have any data here? Well, you do, I see that one.
So 2.4.
The average density was 0.84,
This one?
which is relatively close to the density of polypropylene, but you don't tell me what the actual density is. So you need three numbers in there. One would be your average. Hold on, what? One would be your average from when you added up the 4 samples. Remember in the first question down below, found the density of the smallest, the second smallest, the third smallest, the fourth smallest, and then found their average? That's one piece of data. Second piece of data is the slope of your line. Third piece of data is what is the given value in that table right there. Those three numbers should be in there. By the way, no naked numbers in your conclusion. Naked numbers means you don't have a unit on them. The unit for all of these is grams per milliliter. Jara first, and then I'll get to you, Cynthia. Yes. That's fine. That's all I want. Something along those lines. Cynthia, what can I do for you? Can I tell you if this is right?
I have to add all my like make my numbers not naked, but
Oh, yeah, I use the table.
does that make sense?
Yes. For the slope.
Sure. Guys, here's the thing, and this is, to be honest with you, in your conclusion, you have freedom to kind of do it how you would like. All I need for sure for you in your conclusion is at some point you tell me what the density should have been. This value. My density should have been 1.21. When I graphed it, I got 1.31. When I did the average, I got 1.25. These numbers are all very close together. That's what I need. You to show me or tell me those 3 numbers and then in some way tell me how they relate to each other. Are they close? Are they far apart? Your opinion on that. Okay? But again, use a little bit of common sense. Are the numbers close together? Are they far apart? And did you give me the 3 numbers? That's what I'm looking for. Okay? Questions? If you're done with this, please turn it in now. If you are not, you have until the end of the day today. Okay? I will be around after school. You need help, come and see me. Okay? If you've got it and all you got to do is finish some things up, that's great. But we need to start moving on in class now, ladies and gentlemen. So before the end of the day today, please get this turned in. Now again, in here, remember, I need 3 data points. 3 points of data. What you should have gotten, what you got by doing the average, and what you got by doing the graph, the slope of your line. Okay? Questions? All right. Today then, ladies and gentlemen, we're going to start talking about energy. We're going to start talking about something called kinetic and potential energy. We got an energy activity that we're going to do in a few minutes. It's in your notes. It's not a lab outside of it. It's just in your notes to hopefully get you to kind of physically understand differences between kinetic and potential energy. So that's where we are at, ladies and gentlemen. In your EISN right now, I am on slide 19. This slide, law of conservation of matter and law of conservation of energy. Okay? This is where we are going to start today. So please get here and let's get moving. All right, first of all, these 2 laws are almost identical to each other. The law of conservation of matter and the law of conservation of energy. The only difference between them is one word, matter and energy. Now remember, matter is anything that has mass and takes up space. Okay? Matter is anything that has mass and takes up space. Energy is the ability to do work. That is what energy is. Okay? So when we have the law of conservation of matter or the law of conservation of energy, their definitions are basically the same. Matter cannot be created or destroyed. It can only be changed. Okay? So for example, we could take sodium metal, we could take chlorine gas, and we could put them together. And with a little bit of energy input, we can make salt. Okay? Chlorine gas is a poisonous yellow gas. Sodium metal is a metal that reacts with water by dancing around on the top and bursting into flames. However, when you combine them chemically and change them, they become salt. Okay? That is what we mean when we say matter cannot be created or destroyed. It can only be changed. Energy cannot be created or destroyed. It can only be changed. If I hold this box up in the air, it has something called potential energy, which means that if I release it, it can do what? Fall. That's kinetic energy while it's falling because it is actually moving. Now, how much kinetic energy does it have? It can't have any more than the potential energy that it began with. Okay? But that's what we mean about energy being able to be changed, not destroyed. Same thing is true with matter. Okay? Number 2, what that means is that mass before a chemical reaction has to be equal to the mass afterwards. So if we have a certain amount of things that are reacting, the mass afterwards cannot be any more or any less than it was at the beginning. You can't make any more, you can't lose any. Now, when we say you can't lose any, we have to be careful. Why? Sometimes in a reaction, a gas is created. Where will a gas end up from a reaction? Off into the air. Well, that gas takes with it mass. So sometimes at the end of a reaction, be like, well, there's less stuff here than there was at the beginning, Mr. Brand. You were wrong about that law of conservation of mass. No, we weren't. We just couldn't collect everything that was given off. And if we can't do that, then yes, if some goes off into the air, it's going to change our numbers in the end. Energy before a chemical reaction has to be equal to energy afterwards. Energy before and after also have to be equal. Now, just like sometimes mass ends up in a place we don't want it, sometimes energy ends up in a place we don't want it. Your car, what makes your car go? Gasoline. It has chemical energy in it that it converts to mechanical energy to move your car down the road. However, you only get about 40% of the energy out of the gasoline. Why? The other percent, 60% or however much it is, goes to overcoming things like friction, to making the parts in your car move. Some is lost as heat. So it's not that these things are not there, it's just that sometimes we can't always just add them up real easily at the end. Okay? In physical science, you probably did a lab with the skate park where we looked at the potential and kinetic energy as a skater moved up and down a ramp. Same idea here. Okay? Conservation of matter applies to chemical changes. Conservation of energy applies to any kind of change. If you are going to change chemically or physically, there is a good chance that energy is involved in that change. And that's why we are talking about energy right now. Questions? All right. A few terms for you, ladies and gentlemen. Matter we have already defined, right?
Yeah.
Matter is anything with mass that takes up space, mass and volume. Okay? That is the definition of matter. All right? Do you want me to put them all up there and then talk about them, or do you want me to do it one at a time?
One at a time.
Okay. Mass is the amount of matter a substance contains. The amount of matter a substance contains. This stopper contains a certain amount of matter that makes it the size it is, also makes it the mass that it is. Okay? Now, the amount of matter in this stopper never changes, ever. Well, unless you cut it in half. But otherwise, it is not going to change. Now, as Jera and as Levi are drinking their water or whatever it is that is in their cup, is the amount of water in their cup changing? Yes. But is it going away? No. It's leaving the cup, going into their bodies. Some is leaving and probably evaporating off into the air. But again, all of that matter is still accounted for. Okay? So, what is energy? Oops, sorry. So mass does not change. Now, the hard part about that is people think of living things. Well, aren't we matter, Mr. Wren? Yes, we are matter. Well, doesn't our mass change? Yes, because you're a growing living being. You take in energy. You take in food. You convert that into matter in your body. Okay? That causes you to gain or lose weight depending on what's going on with you. Okay? Energy is the ability to do work. Now, this is the scientific definition of energy. Energy is the ability to do work. Does it mean you do work? No, it means you can do work. So, that is what energy is, the ability to do work. Now, the mass of this stopper never changes. What determines its weight?
Gravity.
Gravity. Weight is the pull of gravity on this object. Now, what is causing gravity on this object right now? Let's hold on to that for a second. Okay? Weight is the pull of gravity on this object. If I put this on a scale, I can find the weight of it. However, if I take this object to the moon and weigh it on the moon, its weight will be 1/6 of what it is here on Earth. So if you or I want to be on the best weight loss program in the world, ladies and gentlemen, let's go to the moon. You'll weigh 1/6 of what you weigh right now on the moon. You weigh 120 pounds here on Earth, you'll weigh 20 pounds on the moon. You weigh 180 pounds here on Earth, you'll weigh 30 pounds on the moon. Now your mass will never change. The amount of matter making you up doesn't. But your weight does. Why? The moon doesn't have as much gravity as does the Earth. So what's pulling on this object right now? The Earth. Pulling this object toward the center of the Earth or toward the ground from where we're standing. Okay? So weight changes depending on the amount of gravity. Weight changes depending on the amount of gravity. Oops, sorry. Gravity is one of several forces of attraction. Can you name me another?
Magnetism?
That's what I was thinking.
Magnetism. Magnetism. Anybody have a third?
Love.
What? Nah, that's a bunch of bull. That's made up by Hallmark. The other one? Force of attraction between opposite charges. Positive and negative. Friction is not really a force of attraction. Friction is caused by forces of attraction. In other words, when two objects are rolling or sliding over one another or moving, gravity causes friction. Okay? But friction is actually trying to overcome gravity. Okay? Force of attraction between the center of mass of two objects. Is this object matter? Is the marker matter? Does it have mass?
Mhm.
Then does it have gravity? It does. Am I matter?
Yeah.
Am I made of mass? Do I create gravity? So how come this marker doesn't fly around me?
Gravity is practically nothing compared to the Earth's.
Correct. The Earth has a much larger pull of gravity than my body does on that marker. Okay? Now, I will give you a little hint here, gentlemen. If you want that special someone, and ladies, if you want that special someone to be attracted to you, take them out into outer space and be the most massive object around, and they will be attracted to you.
I don't think they're going to be attracted.
Well,
They
it'll
will
take-
be.
it'll
If
take-
you are the most massive object around, they will be attracted to you.
it'll take a
So whatever you do, if you're going into space, don't take Mr. Nast with you.
I mean, how are they going to be attracted to you when you die in like the first 3 seconds?
Who said they were going to die in the first 3 seconds? Give them a
Oh,
spacesuit.
Oh,
You don't have to make them, gosh. Right?
You just said take them to space.
So again, whatever the most massive object is in space, other objects are going to orbit around it. Okay? Nadia, what are you laughing about? Nothing? You're the one who's going to rat me out. I'll bet on it.
Are you serious?
I'll bet on it. Because I guarantee you I do this every year. I jokingly make fun of Mr. Nast. And by the end of the day, I'm getting a phone call from Mr. Nast. You're saying I got too much gravity again? Okay? If I'm the most massive object out, you're going to be attracted to me. That is just what gravity is, ladies and gentlemen. Now, you and I, unfortunately, probably will never, ever get to experience being in outer space. So what is always going to be the most massive object around that we are attracted to? The Earth. The Earth. Just the way it is. Okay? Just the way it is. But actually, ladies and gentlemen, is this clip attracted to the metal casing?
Yeah.
What force?
Magnet.
Magnetism. Is it still attracted?
Oh, not yet strongly.
Is it still attracted? That's my only question.
Yes. Yeah.
Cynthia, you're shaking your head no. So you think the magnetism is now shut off?
Yeah.
It's shut off. This knows that I'm no longer close to this and my magnetism shuts off. No. You're right. It is not attracted to it. Why?
This is not close.
Right. So what is it attracted to? The earth. Why? Strongest force always wins. It is still attracted to this metal. And if that were the strongest force, when I release this, it would go flying to here. However, it's not the strongest force. The strongest force is gravity acting on it. So again, now the strongest force is magnetism, stronger than gravity, which keeps it from falling to the ground. Okay? Strongest force always wins. Okay? Love is not a force, sorry. Because you know what a force is? I don't care. Force is a push or a pull. That's what a force is. That is the entire definition of a force. It either pushes things together or pulls them apart.
That sounds like love.
What?
That sounds like love. Yeah.
Oh my God. Get over it already.
I think Zendaya and Tom Holland.
I know love sounds like a force.
Young, naive, and not married, obviously,
You're a
any
married
of you.
man.
What?
You're a married man. You should
I
be
am.
strong of an attraction. Love is marriage is a job.
We'll move on.
Wow. Wow.
No answer.
Okay. Questions. Okay. All right. There are two kinds of energy that we're going to concentrate on first. They are the two most basic kinds of energy. One is called potential. One is called kinetic. Okay. Can anybody tell me what the difference between them is? Before we actually, is it on your slide already? Okay.
Isn't
No.
potential the ability to do work and kinetic is work?
Kind of. Kind of. You are so very close. To have kinetic energy, an object needs to be what? Moving. Kinetic means moving. An object has to be moving. Potential energy is stored energy. Energy that is waiting to be used. Okay? So when we talk about energy that is stored, it can be stored in three ways. By its position, by its deformation, or by bonds between the atoms. Okay? Is the ball moving?
No.
So what kind of energy does it have? Why? Okay. And if I release it, it's going to do what? Fall. What causes it to fall? Gravity, which creates kinetic energy because it then is moving. Okay? Why does the ball bounce back up when it hits the ground?
Has a lot of energy. Because isn't there energy that's stored in the ball when it hits the ground?
Technically no. Well, yeah, kind of. How does it store it? First of all, when I hold it up, that's energy of what? Position, deformation, or bonds? Position. Because it's above the ground, it can fall, right? When it hits the ground, though, what actually happens to the ball, which we can't see because it happens so very fast, is the ball compresses. That's deformation. Okay? That is now stored up energy. And then when it goes back to its original shape, it releases that energy and the ball bounces back up. Another great example of that, bow and arrow. You pull back on a bow, you have put potential energy into it. You can release it, boom, it'll send the arrow flying. Stretching a spring is deformation, or compressing a spring, either way, is deformation. You're storing up energy in there. And then the other way you could store energy is in the bonds of something. strike a match, you're releasing energy as it burns. That was energy that is stored within the bonds of something. Okay? Now, we're not going to worry much about deformation and bonds. We'll talk about it, but we're not going to worry about it as much as we are energy of position. So look around the room and give me something that has potential energy. What? Which one? Why? Because it's up high. It could fall. What else?
Well, I mean, you could name any of the posters.
Any of the posters in this room. Because they are high, hanging on the wall, they can fall. What else?
Well,
Us?
technically,
How?
I know we're on the floor, but like.
Again, yeah, and again, I have people who say, well, Mr. Brandon, we're on the second floor of the building. What would happen if the floor opened up and we all fell down? Okay, you got me on that one. Okay, I'll go with that. Okay, point of reference is important when we're talking about position, though. Most things are not going to fall through the floor of this room, correct? Anything, though, that is above the floor level in this room is considered to have potential energy. Us, it's kind of tricky because if you're standing on the floor, technically you don't. But again, if you're saying you could fall out of your chair, okay, I'll let that go. Okay? What does potential energy depend on? It depends on mass and height of the object. It depends on the mass and the height of the object. How high the object is above the ground, how heavy the object is, determines how much potential energy you have. Now, I will never make you calculate potential energy, but I'm going to give you a formula anyway. And it is potential energy is equal to mass times gravity times height. Now, while I will not make you know what this formula is, I will ask you what are the factors that can affect your potential energy. Now, which one of these will we never see or we will never experience changing? Gravity. Unless we're lucky enough to go off into space. I was getting to this earlier and it just reminded me of what I was going to say. Far away from the door, is this still attracted to it? We've determined that, correct?
Mm-hmm.
But now at a further distance, that force is not strong enough to attract it anymore. But it's still attracted, correct? Here's another good weight loss program for you, ladies and gentlemen. Get on a plane and fly. Why?
well, you're further away from Earth.
You're further away from Earth, which is what you are attracted to. So technically, when you're flying in a plane, you will weigh less than when you're on the ground.
Is that why pilots are always so skinny?
No. It has nothing to do with that. And here's the thing. As soon as you're done flying and you come back to the ground, boom, weight's going to be the same. But the further you would get away from Earth, the less gravity you would feel. Just like the further I get away from the door, the less attraction this feels to it. Technically, you climb a high mountain, you'll weigh less on the top of a high mountain than you will down at Earth, at sea level. Okay? Now, you may not be able to notice it, you may not be able to detect it, but technically that's what happens. Units are joules. Joules are the units. Okay? Joules are the units. Now, energy is energy. I don't care what kind of energy. Energy is energy, which means everything that is energy could be measured in joules. Now, we don't with some things. For example, when you eat, what do we measure the energy in food in? Calories. You could convert from calories to joules, though. It's not a hard conversion. 4.184. Okay? Kinetic energy is energy of an object that is moving. Has to be in motion. Has to be moving. Okay? If it is moving, you have kinetic energy. If it is not moving, you don't. So what variables affect kinetic energy? Why would an object have more kinetic energy?
Speed.
Nope.
I don't know.
What?
Speed.
If it's moving, speed has got to affect it. What else?
Wait.
The mass. The mass. We use the term velocity because velocity is speed and direction. Understand it's basically the same thing, almost. Okay? got a formula for you for kinetic energy. 1/2 mv squared. M being the mass, v being the velocity, and you square the velocity. What's the unit? Joules. Joules. I know you thought I ran away and left you. I didn't. Okay. We're going next door for this next activity, ladies and gentlemen. I just went over and tried to turn the projector on in Mr. Hart's room, but it's not working. We are going to do the next 2 slides over in Mr. Hart's room. Okay? We are going to look at kinetic energy. And we are going to do it by testing 2 variables. Mass and velocity. Velocity is how fast an object is moving. Mass is how heavy the object is. So in Mr. Arts' room, on the desk, in the back, I have 3 books. You will notice that one of them is very heavy, one of them is very light, and one of them is somewhere in the middle. That's how we are going to get our 3 masses. And what you are going to do is you are going to stand on one side of the table, your partner will be on the other, and you are going to push the book to them at as constant a speed as you can. Now this is difficult to do, but you're going to try to do it. You're going to push it to them at a constant speed. And the person who it's pushed at is going to determine which book is the easiest to stop and which is the hardest. So you are going to rank these 3. Easiest to the hardest. I don't care if you use 1, 2, and 3. Easy, hard, medium, whatever. You are going to rank them. Okay? Now, the one that has the most kinetic energy, is that going to be the easiest to stop or the hardest to stop? That's going to be the hardest to stop. So when you're doing this and we get one that is stopped easily and one that is not, that is what we are looking at it for. Let's try to get something done. Okay, sorry, ladies and gentlemen. Here we go. So, the second time, same exact experiment. You're sliding a book across the table to your partner, but you get to pick which book. Only pick one of them. You want to do the heavy one, the medium, or the light. I don't care which one, but now you're going to throw it slowly across the table, medium speed across the table, fast across the table. Try not to kill your partner. Okay? And again, you're trying to figure out which one is the easiest to stop. Which one is the hardest to stop. Okay? And then over here, when we increase the mass, the kinetic energy did what? So here, when you're looking at comparing these, the heavier mass, how is its energy compared to the lightest mass? And then here, when we increase the velocity, the kinetic energy did what? Was it more kinetic energy when the velocity was higher, or was it less? So you're going to fill this in. Questions? Okay, go to the next slide real quick. Okay, now, for the next slide, we're looking at potential energy. So again, we are using the same 3 books: heavy mass, light mass, medium mass. You are going to take and drop them from the same height to your partner. From the same height, you are going to drop them. They are going to catch them, and they are going to try to determine which is the easiest to stop, which is the medium one, and which is the hardest one to stop. And now again, the one that is the hardest to stop has the what potential energy? Not kinetic now. Had the most potential. Okay? Had the most potential. Then we are going to test the height. So you need to pick one of these three again, and then you need to drop it to them at 3 different heights. We will show you how to do that, and then again you are going to answer these 2 questions. Does anyone have any questions? So there are 17 of you in here. You have to work with a partner because you can't throw it and pass it to yourself. So there will be one group of 3. Bring your computers with you. Come follow me. And I want to show you where we're going to do this and exactly how. So that way if somebody shows up, they know we're next door. Let's go. Let's go. Let's go.
Pues se graduó, no siguió estudiando.
Come in here real quick and we will show you what you are going to do. All right, Nadia, you ready? Move your computer. So, here's what happens. Please watch. The first time I'm going to send the book across the table at Nadia, she's going to stop it. I'm going to then go to a smaller book, try to do it at the same speed. She's going to stop it each time. Ultimately, she's going to make a decision, and if she wants to do it, Cynthia then catches. You are going to make a decision which one was the easiest, the hardest, and the least hardest to stop. Second time, you only pick one of the 3 books. I'm going to throw it with low velocity, medium velocity, ready? High velocity, which is the hardest to stop. Second time, I'm right over here, Darby. Put your hands up straight in front of you. Now, close enough that you can catch this. Okay? I'm going to hold it at the same height, right above her head. Then I'm going to switch to the next book, same thing, then the next one. All at the same height. Pick one. Which one do you want to do for last? That one? Okay, come here. Stand right here. Right around there. So you need to get some height for this one because we want different heights. Ready to catch it? Okay, that'd be 1. Give it back. 2. 3. Figure out which one is the easiest to stop, which one is the hardest. Go to work, please. There you go. Yeah, when is Nadia ever going to get a chance to throw a book at your face? Ever. Ever. She wants to do this. Go ahead. Good. For real, Cynthia, she wants to wipe you out. Now, you're just ranking. If you want to make 1 the easiest, 3 the hardest, or if you want to put easy, medium, hard to stop, that's fine. However you want to do it. Please make sure you don't wipe out your partner's computer when you're passing the book across the table. You can do it very easily. The main thing is that you understand the experience. It's up to you. You can make 1
changing the velocity, you're not changing the mass of the ball. She can't even tell. Remember, you're always just ranking them. I don't care how you rank them. If you use numbers, if you use medium. Yes, but it's all from the same height. Same mass, but now you're going to hold a different speed. Slowly, the medium speed and the fast speed. Any one of your three. Alright? On that line, you tell me which book you use. You provide the medium or fast. Well, we're judging on the kinetic energy increase, but how easier or harder is it to stop? If it's harder to stop the book, then probably you should pick one. If it's easier to stop the book, then it's less energy. Okay? So that's why we're changing that so that we can judge, okay, if the object is harder to stop, more energy is required to stop, and it's harder to stop. She just wants to drive the book. That's the way it works. So you're telling me, okay, but again, stand in between there. Okay, ready to stop this? Ready?
Oh, very nice. Very nice.
Because it was what? Yeah, same weight, right? Same mass. That didn't change. But when it moved faster, it became harder to stop. So that means that it probably had more momentum. It reads motion. I did the video. I don't know why they call it the same. I didn't know. Well, all areas. So you should be able to know something. Okay, so one is that the easiest way to harness. Okay, so what we find is that okay, so as we increase the mass, the kinetic energy increases as we move harder to stop. So I know this because something along that line, right? You need a reason, right? And why are you doing that? It's 3 feet. long as you're higher.
Well, you're not gonna get any higher than that.
Oh, sure, we pick a desk. You know how strong these are? That desk is gonna break.
I don't know how much you weigh.
I think she's trying to throw it in your face.
I think so.
Oh.
You're like right here. No, that was right there. You're like right here. I want to get ready for that.
You realize that's why things are taped up, because people drop them. Then you should have picked the lighter book.
Okay, but we did.
At least it wasn't that.
Wow. Catch the ball! Wow. Especially the ancient ones that are 20-some, 40-some years old. What year is on there? Okay, that book is 42 years old. Have some respect for your elders. It's still respectful. Okay. When you're done, put all 3 books back on the cart over here, ladies and gentlemen, and then you can head back to our room. 3 books on the cart, please, and then you can head back to our room. Thank you.
The book had too much kinetic energy.
Apparently. Oh.
You know when I sat in that box, I was like, why did that put me in?
Why did we do that?
I was like,
And you got the door led to Mr. Archer.
It was like all over.
I thought there was like a little I figured it out.
I understand that. We can use
Oh,
everybody. Which, yeah, well, it makes sense. You need more space. And your
And
room
then
is not really set up.
Who's laughing?
Yeah. By the way, it's a good thing Tom's not here. He would die if he looked at his phone right now. No, it's just,
Oh, yeah.
yeah, he would be rolling over in his grave. So,
His graves.
he's not dead yet, but okay. All right, ladies and gentlemen. So, hopefully you have an idea of what is happening here. Okay? Now, if we go to the next slide. Now, here's what happens on this slide. Kinetic energy. If we increase the velocity, if we threw whatever book you threw harder across the table, what happened to kinetic energy? Did it go up or down? So what I want you to do is take one of these 2 arrows, the up arrow, and put it here next to this. So if velocity increases and mass is constant, kinetic energy will go up. Which then means if velocity decreases, but the mass is constant, what will happen to kinetic energy? It'll go down. Okay, what kind of relationship is this? So all you do is click on the box that says inverse and delete it. Okay?
Click on the box that says inverse and delete it. So now that is what our relationship is. Okay? Now again, Cynthia said something really insightful when we walked over there, which is that this is basically what? Common sense. You're right. Physics is a lot of common sense. You're right. Okay? If I take a bullet and I throw it at you.
A bullet?
A bullet.
You're gonna throw a bullet?
Throw a bullet at you.
Oh,
Are you worried?
No.
Now I fire it out of a gun at you. Are you worried?
maybe a little bit.
Well, wait a minute. It's the same mass. What's the difference?
Velocity.
The difference is velocity. And by the way, here's where velocity is important and not just speed. Because velocity is speed and direction. So if I point it at you,
It's a little scary.
that's more important than if I point it at the wall, correct? Okay. So, again, you are absolutely right, Cynthia. And I said this. Most of physics, about 90% is common sense. So when you take physics, 90% of it is common sense. Okay? It's the other 10% that gets important. Okay? So again, in terms of kinetic energy, if velocity increases, the kinetic energy will increase. An object that is moving faster can do more damage than an object that is moving slower. Okay? So how about mass? What if we change the mass? What happens if the mass goes up but the velocity stays the same? So now I throw a bullet at you and then I throw a 16-pound bowling ball at you. What happens to the kinetic energy as the mass goes up?
Goes up.
It goes up. I know this is common sense, I know, but we still need to make sure you understand it, right? Okay? So then what happens if the mass goes down? Kinetic energy goes down. Well, what kind of relationship still? That is still a direct relationship, ladies and gentlemen. Okay? That is still a direct relationship. All right. Two more. So now we're going to talk about potential energy. Now we're dropping the books from the same height, but we're increasing the mass of the books. As the books got heavier, what happened to the kinetic or potential energy? It went up. It increased. So if the mass goes down, potential energy goes down. What kind of relationship? Still a direct relationship. Still a direct relationship. Okay? So, have you ever heard the old story? Well, if you drop a penny from the top of a tall building, it can kill somebody?
No, I'm not that.
It can't. It can't.
What, can it?
No.
Oh.
Why? It doesn't have enough mass. Even though it may fall from a long distance, it doesn't have a lot of mass. Somebody throws a feather at you really hard. Do you jump out of the way? No. It doesn't have much mass, so it can't have a lot of energy.
What do you do from the top of the bridge?
What?
What do you do from the top of the bridge?
It's still not going to kill you because of the limited mass of the object, it cannot bring with it a lot of energy. Now, tomorrow we'll talk about what happens if you drop a heavy object.
What if I
Now, we've got a different situation. Have a great day, ladies and gentlemen. Go away. See you tomorrow. Christian, please be on time tomorrow. Come on, dude. Okay? We got a lot of catching up to do, and I want to see you get it done because otherwise, man, I'm not that much fun the next year again.
You said you're gonna be here after school?
I will be, yes.
Because I'm getting a little bit of help from my old student lab that I'm missing.
Okay. Come on in. I'll be here. 212? No, take that down. Hand that to me, please. Sorry. That was my last hour. That was these guys. I can't let them stay in here too long. They screw around, and then I got to move them to a different area. Hey, way to remember your coat today. I noticed. I noticed.
Brianna Guzman, please report to student
Let me do
services.
me.
Brianna Guzman, to student services. Thank you.
This nigga got told.